Hello everyone. I'm Jaemin Na from the University of Azu in Korea. Today I'm gonna talk about FixBi framework for unsupervised domain adaptation. First, let me introduce a little bit about what domain adaptation is. Generally, the goal of domain adaptation is to train models on a labeled source domain and generalize these models for a target domain that has different data distribution. Depending on the label of the target domain, it can be divided into several scenarios. But in this work, we care only about unsupervised domain adaptation where we have no labels in the target domain. Many of the previous methods performed adaptations directly from the source domain to the target domain. However, when the domain discrepancy is large, these methods may be inefficient. So we propose to use augmented domains between the source and target domains for efficient domain adaptation. Now we go through our methods. In most previous studies, random values from the beta distribution have been used as mix-up ratios, but we propose to use a fixed ratio-based mix-up. Here, we use two types of fixed ratio-based mix-up. One is a source-dominant mix-up and the other is a target-dominant mix-up. With these two types of mix-ups, the two models are trained with each different mix-up ratio. The most important thing here is that we construct two models with different perspectives using our fixed ratio-based mix-up. Secondly, we introduce a confidence-based learning method. This time we only use the target samples, not the mix-up samples like before. According to the confidence threshold, we divided the pseudo-labels into positive pseudo-labels and negative pseudo-labels. If one network assigns class input probabilities above a certain threshold, then this predictive label is considered a positive pseudo-label. The positive pseudo-labels are pretty reliable, so this allows the two models to learn from each other. Moreover, since our method gets results from both networks for the same input, bidirectional matching is possible. Conversely, the negative pseudo-label indicates the most confident label predicted by the network with a confidence lower than the threshold. These negative pseudo-labels are unlikely to be correct labels. We need to increase the probability values of all other classes except for these negative pseudo-labels. Finally, we introduced a new consistency regularization method. We used exactly the same fixed ratio-based mix-up to ensure that both models maintain consistency in the same mid-area. It can help to construct the domain bridging by ensuring convergence and stability of training. In the experiments, we extensively analyzed our methods on 3 domain adaptation datasets. First, we can observe that the two models trained with only our fixed ratio-based mix-up have different strengths and weaknesses. After trained with our fixed ratio-based mix-up, these two models have similar average performance, but they have quite different aspects in terms of class-wise accuracy. Looking back to our confidence-based learning, for a confidence threshold, the basic strategy is to set a fixed value as a hyperparameter. However, a deep neural network tends to start at a low level of confidence value and its value gradually increases as the network learns. The fixed threshold cannot properly reflect the confidence which is changed constantly during training. Therefore the number of positive and negative pseudo-labels can be biased to one side. To overcome this problem, we adopt an adaptive threshold which is changed adaptively by the sample mean and standard deviation of a mini-batch, not a fixed one. We observe that the confidence of the target dominant model rises sharply at 100 epochs, which is the point that we start to apply the confidence-based learning method. We conducted comparative experiments of our fixed ratio-based mix-up with other types of ratios and showed that our proposed method is effective, and we also investigated the effects of our proposed components. We also achieved state-of-the-art performance on 3 domain adaptation benchmarks. In conclusion, we proposed 3 main contributions. We proposed a FixBi algorithm that bridging the domain spaces to deal with the large domain discrepancy problem in an unsupervised domain adaptation scenario. Our main methodology is to construct an intermediate domain with different characteristics between the source domain and the target domain. We completed this through our fixed ratio-based mix-up with different mix-up ratios, and further proposed bidirectional matching, self-penalization, and consistency regularization for efficient use of intermediate space. And we also achieved state-of-the-art results on domain adaptation benchmarks. Thank you for watching our video. If you are interested in our work, we recommend to check out our paper. Thank you.